question 6 of the matter and radiation pack. We have a table of data, 4 different nuclei with some neutrons and a nucleon number. The first question wants us to work out which nucleus contains the fewest protons. So I think the easiest way to do this is to actually add another column over here, which would be the proton number. Remember, to work out the proton number is simply our nucleon number take away our number of neutrons. So 11 minus 5 in this case, that's going to give us 6. And if you do the same for the others, that's going to give us 5, 6 and 8. So this makes the next question quite easy. Which nucleus contains the fewest protons? It is, of course, nucleus Q with 5 protons. 1 mark. Part 2. Which 2 nuclei are isotopes of the same element? So an isotope is an element which has the same number of protons but a different number of neutrons. So I'm going to be looking for the 2 numbers which are the same here in my proton column, which is going to be 6. So that means we've got P and R are going to be the same. Part 3. State and explain which nucleus has the smallest specific charge. So remember, specific charge is the ratio of the charge to the m. I'm not going to convert to standard units for this one. I'm just going to work out the ratio of these. So we've basically got 6 over 11 for nuclei P, 5 over 11 for Q, 6 over 14 for R, and 8 over 17 for S. Now you should be able to tell from here which is the smallest one. It's 6 over 14. If you can't, you could work all these out as a ratio, and that will give you 0.43, which is the smallest one. So it's definitely nucleus R. Okay, moving on to the next page. Bring this up. Complete the following equation to represent beta minus decay of nucleus R to form nucleus X. So with beta minus decay, we are increasing the proton number by 1. A neutron is turning into a proton, and the nucleon number doesn't change. So the bottom number is going to go up to 7. Top number is going to remain at 14. And then, because we've increased the proton number by 1, we've got to compensate that with an electron which has a negative charge, or a beta minus particle. That sorts out the conservation of charge, but we also need to conserve lepton number. So lepton number over here is 0. That is 0, no leptons. This has a lepton number of 1, so it needs something with a lepton number of -1, which has 0 charge, which of course is the anti-electron neutrino. Part B. Strong nuclear force is responsible for keeping the protons and neutrons bound in the nucleus. Describe how the strong nuclear force between 2 nucleons varies with the separation of the nucleons, quoting suitable values for separation. So I'm not going to write this out, but the bullet points you're looking for, it's a short range. Strong nuclear force only acts within the nucleus. It has a very, very short range. Even across the diameter of a large nucleus, the range starts to diminish quite considerably. So it's repulsive, and that is at very, very close distances. So at any sort of distance smaller than about 0.5 femtometers. Femtometers is 1 times 10 to the minus 15. And then it becomes attractive at distances kind of greater than that. So anything at about 0.2 femtometers and upwards, then it starts to become attractive. On a graph, I'll just sketch this out, that means that it's attractive at very short ranges and then repulsive, and then it dies to 0 at longer ranges. So if this is the force on this side, we've got attractive force down at the bottom there, and we've got repulsive force at the top, and this is of the order of femtometers, very small. Part 2, another significant interaction acts between the protons in the nucleus of an atom. Name this interaction. Well, we've got lots of protons which are positively charged, so the interaction is going to be the electromagnetic. And the next bit wants to name the exchange particle. It is the photon, which carries no charge. And that is 12 marks.